In the freezing Swiss Alps, where mountain cliffs rise almost straight up, a massive transportation system hangs suspended in midair, held in place by only a few steel cables stretched across kilometers of open space with a slope approaching 60 degrees. This is the steepest cable car ever built in the world, pulled almost vertically up the rock face. But the most astonishing part lies behind the scenes. On this extreme construction site, workers must suspend themselves thousands of meters above the ground, installing each pulley, each bolt, and each steel cable, a place where even the smallest mistake leaves no second chance. But here's what the tourist brochures never mention. The first cable installation attempts ended in disaster. Cables snapped during tensioning. Workers fell from suspended platforms. Helicopter lifts failed in sudden wind gusts. The engineers who survived these early catastrophes discovered techniques that would revolutionize high-altitude construction forever. Welcome to Macroforge, where we explore infrastructure built on Earth's most extreme edges. If engineering that defies gravity and freezing conditions fascinates you, subscribe now. What you're about to witness will change how you understand mountain transportation. This cable car line is called Steckelberg-Mühren, located in southern Switzerland, one of the most rugged mountain areas in Europe. Stretching over 1.1 kilometers and climbing nearly 800 meters in elevation, the system pushes cable car engineering beyond traditional limits. 2 cabins, each capable of carrying up to 85 passengers, travel along a route with a maximum gradient of 159%. A level so extreme that very few transportation systems anywhere in the world attempt it. What makes this project truly remarkable, however, is not just the numbers or the records it breaks. It's the way engineers build, install, and operate a suspended system in fierce winds, heavy snow, and terrain where even the smallest mistake is not an option. But before any cable could be hung, they needed to see through the mountain itself. The first step in building this cable car line is the design stage on paper. At this point, experienced engineers must calculate every factor that could affect the system: the steepness of the cliff, the height and position of each tower, extreme wind forces, cabin load, cable tension, and even small vibrations as the cabin moves. This is not a job for ordinary engineers, but for highly seasoned specialists, because even a tiny error on the drawings could make the entire system unsafe to operate. In the end, they chose a 60-degree incline. It's a bold decision, but the only design that truly fits the terrain at the destination. But calculations on paper meant nothing without a construction site. What came next required attacking solid rock. Immediately after the drawings are finalized, the engineers move to the construction site, thousands of meters above sea level, where the terrain is extremely steep, solid bedrock is exposed, and natural flat ground is almost non-existent. To make construction possible, they had to use controlled blasting to create a flat construction site. They must precisely calculate how much rock needs to be removed, how deep to drill, and how much explosive energy is required to lower the terrain exactly to the design level. Drill holes are arranged in a grid spaced from just a few dozen centimeters to over a meter apart. Each hole contains a carefully calculated amount of explosive, so the rock breaks in the intended direction without causing widespread vibrations. The blasts are triggered in sequence rather than all at once, allowing engineers to control the force and prevent cracking in the surrounding rock mass. Afterward, all broken rock is cleared away, the surface is leveled, and its load-bearing capacity is thoroughly checked. Only when the foundation reaches the correct elevation and stability can the cable car project move on to the station construction phase. But building at this altitude presented a logistics nightmare. What came next created an aerial supply line. Once the site meets all requirements, construction of the cable car station can begin. However, at an altitude of several thousand meters, there are no access roads for trucks or large cranes. As a result, all materials must be transported using a temporary cable car system. Building this temporary cable line also takes considerable time, but it operates in much the same way as the main cable car system. This temporary line works like an aerial logistics system. Each trip can carry between 1 and 3 tons of materials depending on wind conditions and the length of the cable span. Steel beams, cement bags, formwork, and even small machines are secured to pallets, suspended beneath the cable, and slowly moved across steep cliff faces with transport distances stretching hundreds of meters over sheer terrain. Each trip typically takes 20 to 40 minutes to deliver materials to the site. Every lift must be carefully planned around load limits and weather conditions because at this altitude, strong winds can cause suspended loads to swing dangerously. But materials delivered were useless without foundations. What followed anchored everything to bedrock. Now, the construction of the cable car station officially begins. First, the construction team precisely sets out the building's center line, defining the foundation zones and the main load-bearing points. From there, foundations are excavated and drilled deep into the bedrock, and steel anchor rods are installed to firmly tie the structure to the mountain. Once the foundations are secured, reinforcing steel is installed exactly according to the drawings, forming the load-bearing framework for the foundations, floors, and equipment platforms. Concrete is then poured in stages with careful compaction and strict control of time and temperature to achieve the required strength under cold mountain conditions. After the concrete reaches sufficient strength, the formwork is gradually removed and structural elements such as beams, floors, and load-bearing walls are constructed, creating the main structural frame of the station. On top of the structure, large steel bases and support frames are installed to prepare for the cable system, sheaves, and mechanical equipment. All elevations and tolerances are carefully adjusted because at several thousand meters above sea level, repairs are extremely difficult. Once the structural frame is complete, the station moves into the exterior cladding and enclosure phase. Metal panels, glass, and protective materials are installed to shield the building from strong winds, heavy snow, and ice, while also reducing the impact of harsh weather on the equipment inside. But the station was just the anchor point. What came next would become the system's lifeline. Next, we entered the steel cable manufacturing plant, the heart of the entire cable car system. Here, high-strength steel is drawn into thin wires with precise diameters, then wound onto large spools. Multiple small wires are then twisted together in a predefined pattern to form cable strands that can withstand enormous tensile forces while remaining flexible. During the twisting process, the tension of each wire is continuously controlled to ensure the load is evenly distributed throughout the cable. After that, the cable passes through pressing, compacting, and geometric adjustment systems to stabilize its internal structure. Some cables are also lubricated or coated with protective layers to reduce friction, resist corrosion, and extend their service life in harsh environments. Finally, each massive cable reel undergoes strict testing for strength, elongation, and dimensional accuracy before leaving the factory, ready to become the backbone of the entire cable car line. After manufacturing, the massive steel cable reels are transported from the factory to the cable car construction site by truck. Each reel can weigh several tens of tons, so heavy-duty cranes are used for loading, and the reels are firmly secured on specialized loaded trailers. The trucks move at controlled speeds along pre-surveyed routes to handle the extreme weight and size of the cargo. As they approach the mountain area, drivers must navigate narrow roads, sharp turns, and strict weight limits. Even though the factory was only about 40 kilometers from the construction site, the transportation process took up to a week. But cables alone couldn't support themselves. What came next held them in the air. Next, we moved to the factory where the cable car tower components are manufactured. Instead of being built as a single piece, each tower is produced from multiple individual steel modules, fabricated in the factory with extremely high precision. Every section is machined, pre-drilled for bolts, and carefully measured to ensure that all parts fit together perfectly once they reach the construction site. Afterwards, these modules are transported from the factory to the base of the mountain, where they are staged and prepared for lifting operations. Because the terrain is steep and inaccessible to vehicles, each tower section must be suspended beneath a helicopter and flown to its installation point on the mountainside. At the construction site, the cable car tower is assembled from the ground up, with each steel module carefully lowered into position by crane or helicopter. Once in place, every module is secured using hundreds of high-strength bolts tightened in a specific sequence and to precise torque values. Before the next section can be installed, the construction team must measure and adjust the tower's vertical alignment using specialized surveying equipment. Even a very small misalignment at the base can be amplified dramatically as the tower reaches its full height. Once the tower structure is complete, the installation of the cable support frames and load-bearing components at the top of the tower begins. The cable guide roller assemblies, each weighing from dozens to hundreds of kilograms, are lifted into place and installed one by one. Their position and elevation must be adjusted with extreme accuracy so that the steel cables can pass smoothly without misalignment or excessive wear. But towers standing couldn't move cabins. What came next created the actual transportation system. Next comes the cable pulling process. Cable installation does not begin with the main cable itself, but with a smaller, lighter, temporary rope. First, this temporary rope is lifted into the air using a helicopter or pulling equipment, then guided through the towers and stations to create an initial path. Using this temporary rope, the construction team gradually pulls in larger and heavier ropes, step by step, increasing size and load until it is strong enough to pull the main cable. Once the main cable begins to enter the line, high-capacity winches are installed at the station to control the pulling force uphill, while braking systems at the opposite end prevent the cable from sliding or sagging excessively. Throughout this process, the cable must remain suspended in the air without touching the ground or the rock face. The pulling speed is extremely slow and continuously monitored because every meter of cable carries enormous loads. When the cable has been pulled to its full length, both ends are brought together in preparation for forming a continuous loop. But pulled cable needed permanent connection. What followed required working suspended in open air. After the main cable has been pulled into its final position, the next stage involves handling, alignment, and splicing directly along the line. Workers must move along suspended work platforms hanging high above the ground, protected by safety nets on both sides. Here, the steel cable is kept under controlled tension while it is straightened, untwisted, and guided into its correct working position. The two ends of the cable are then brought together in preparation for manual splicing, a process that requires exceptional precision and experience. The splicing itself is carried out directly on the line with each bundle of steel wires carefully separated and interwoven according to a predefined sequence. Once the cable is placed under tension, the individual wires tighten against each other, forming a continuous loop with no mechanical weak point. But cables alone couldn't carry passengers. What came next housed the travelers. Next comes the cable car cabin manufacturing process, which is carried out entirely in the factory before the cabins are transported to the mountain. The cabins are not built from a standard template, but are custom designed for each route based on factors such as load capacity, operating speed, and local wind conditions. The cabin frame is manufactured from aluminum alloys and lightweight steel, providing high structural strength while keeping overall weight as low as possible. Once the frame is complete, exterior panels, flooring, safety glass, and door systems are installed directly onto the structure. At the same time, the suspension system, damping components, and connection points to the cable are assembled and precisely adjusted before leaving the factory. Each cabin undergoes a series of inspections to verify structural strength, sealing, and operational safety. Only after meeting all required standards are the cabins packaged and prepared for transport to the construction site, where they will later be installed on the cable car line. After manufacturing is complete, the cable car cabins are transported from the factory to the base of the mountain using specialized vehicles. In areas where there is no road access, the cabins are then lifted by helicopter and flown closer to the station or installation points along the line. Before being mounted onto the cable, each cabin undergoes a final inspection of its suspension system, connection points, and safety components. The cabin is then lifted and attached directly to the cable, a process that requires precise alignment to ensure proper balance and prevent twisting. But cabins attached meant nothing without power. What came next made everything move. Once the mechanical installation is complete, the electrical and control systems are installed. Power cables, sensors, and communication lines are routed through the station and along the cable line to connect drives, brakes, and safety devices. Control cabinets are assembled and wired, integrating the main drive system, backup power, and emergency braking controls. Software and control logic are then configured to manage speed, acceleration, and safe stopping under different operating conditions. All systems are carefully tested step by step to ensure accurate signal transmission and reliable response. At the heart of the cable car system is the drive unit, which provides the power needed to move the cable and cabins along the line. This system typically consists of high-power electric motors, a gearbox, and large drive sheaves that transmit torque directly to the cable. The drive system is designed to operate smoothly under heavy loads while maintaining precise speed control. Multiple braking systems are integrated to ensure safe stopping under normal and emergency conditions. But completion wasn't approval. What came next proved the system could survive. In the final stage, the cable car system enters the testing and commissioning phase. The line is first run without passengers to check cable tension, drive performance, braking response, and system stability under different speeds. Gradually, test loads and empty cabins are added to simulate real operating conditions. Engineers monitor vibrations, wind behavior, and emergency systems to ensure everything performs within design limits. Only after all tests are successfully completed is the cable car officially approved for passenger service. Europe's engineers built the steepest cable car on Alpine cliffs stretching 1.1 kilometers, climbing 800 meters elevation with 159% maximum gradient, carrying 85 passengers per cabin on a 60-degree incline, using controlled blasting to create platforms at thousands of meters altitude, transporting materials via temporary cable cars carrying 1 to 3 tons, taking 20 to 40 minutes per trip, drilling foundations into bedrock, installing steel anchor rods, pouring concrete in staged compaction under cold conditions, manufacturing steel cables through precise wire twisting testing for strength, elongation, and dimensional accuracy, transporting tens of tons reels taking 1 week for 40 kilometers, fabricating towers as multiple steel modules lifting via helicopter to mountainside, securing with hundreds of high-strength bolts, installing cable guide roller assemblies weighing dozens to hundreds of kilograms, pulling cables using temporary ropes step by step, maintaining suspended air position, performing manual splicing on suspended platforms, custom designing cabins from aluminum alloys and lightweight steel lifting by helicopter to installation points, installing high-power electric motors, gearboxes, and drive sheaves, integrating multiple braking systems, testing cable tension drive, performance braking response. From design calculations through helicopter lifts to manual splicing, this proves vertical terrain isn't impossible. It's engineering waiting for determination. What impressed you most? The 159% gradient? The manual cable splicing? The helicopter tower lifts? Drop your thoughts below. Thanks for watching Macroforge, where cliffs become transportation and cables become lifelines. See you in the next one.